I'm Ryo. I'm from NTT Tokyo. Let's start. Okay, so this is the outline of my talk. I first explain cryptography and quantum information a little bit, and the second, I will give a definition of secure key leasing, or what is secure leasing, and then I move to how to achieve public key encryption with secure key leasing, and finally, I a little bit explain other constructions with secure key leasing. Okay, so let's consider the following scenario. So a company hire many employees. There are many employees, and to give access to some confidential information to the employees, the company give a secret decryption key. The company leases a secret decryption key to employees. And to read the confidential information, employees use the leased decryption keys. Okay? And at some point, an employee leaves this company. Then the company requires employee to return the secret decryption key. Then the employee, okay, I return the secret decryption key to the company. Okay. But of course, the employee can keep a copy of this secret decryption key because it is digital information, so we can copy as much as you want, right? So there is no guarantee that the employee deleted this secret decryption key. And yeah, this is a limitation of classical cryptography because we cannot prevent from copying classical information, digital information. So this, we want to achieve some kind of secure leasing, but it is impossible by classical cryptography. Okay? So this is a motivation. However, we can use, in the future, maybe we can use quantum computers, universal quantum computers. And as Giulio and Omri explained, there is a famous theorem, no cloning theorem in quantum information theory. So there is no general procedure for copying all unknown quantum states. So this is very nice. And maybe by using this theorem, we can go beyond classical cryptography. I mean, so maybe we can achieve what classical cryptography cannot achieve by applying this theorem. Okay? And the answer is yes. We can actually go beyond the classical cryptography by using quantum information. Let's see. So there are a lot of quantum cryptographic primitives. In this morning, as Omri explained, there is quantum money, which means that we cannot make a copy of quantum banknote. Okay? And we also have unclonable encryption, which means a ciphertext is quantum state and cannot copy this quantum ciphertext. And we also have a single decrypted encryption, which means a secret decryption key is also, we cannot copy a secret decryption key. It is unclonable secret decryption key. And we have encryption with certified deletion, which I will explain tomorrow's morning talk. This means that a ciphertext is a quantum state, but we can delete this quantum ciphertext and generate a classical certificate that guarantees that this ciphertext is deleted. And the secure key leasing is secret decryption key is a quantum state. And if we return this quantum decryption key, then after that, the user cannot decrypt ciphertext anymore. And this is what I'm going to explain from the next slide. And we also have tokenized signature, as Omri explained in this morning. After we generate a signature by using a quantum signing key, then this signing key destroyed. So we have many great cryptographic primitives by using power of quantum information. And okay, so today I will explain secure key leasing, and I will explain certified deletion tomorrow. So in this slide, I explain the difference between secure leasing and deletion. Functionality is very similar, but in certified deletion, I mean that some cryptographic object. Here is the example is a decryption key is a quantum state, and we can delete this quantum decryption key and generate a classical certificate that guarantees that this quantum decryption key was deleted. And we can verify this classical string by using some verification algorithm. On the other hand, secure leasing means that we don't have a deletion algorithm. In secure leasing, a certificate is quantum state. Here is this example. Quantum decryption key itself is a certificate. So if we return this quantum decryption key, then we can verify that whether this returned decryption key is valid or not. This is the difference between secure leasing and deletion. Okay. So now let's see what is secure key leasing. And I focus on public key encryption with secure key leasing in this talk. There is okay, so a quantum computer generates public encryption key EK and secret quantum decryption key DK, which is quantum state. And we also generate a verification key, VK. And this, okay, like in the previous example, the company send a secret decryption key to a user. And a sender generate encryption of plaintext M1 by, oh, sorry, this is not PK, it is EK. Generate encryption of M1 by using public key EK and send the ciphertext to the user. Then this user can decrypt this ciphertext by using this quantum decryption key. And at some point, this user returned the secret decryption key to the company. And if this company successfully verify this returned decryption key is valid, then after that, even if this user is given encryption, another ciphertext of plaintext M2, then this user cannot decrypt this ciphertext anymore. This is public key encryption with secure key leasing. So far, so good? Okay. So now let's move to the more formal security definition of public key encryption with secure key leasing. So the challenger generate encryption key and decryption key and verification key. And first, this challenger send public encryption key and secret decryption key to the adversary. And the adversary has access to the verification oracle, which returns valid or invalid when the adversary sends possibly malformed decryption key. Here is possibly malformed decryption key is DK2. And the adversary can try this malformed decryption key is valid or not by using verification oracle. And the adversary at some point send two challenge plaintext to the challenger. Now I focus on the indistinguishability security. The challenger flip a coin, B, 1-bit coin. And if the challenger verifies that given decryption key is valid by using the verification key, then the challenger generates a challenge ciphertext by using one of the two plain texts based on the chosen coin, and send the challenge ciphertext to the adversary. Then the adversary tries to guess the selected coin. And if we consider one-wayness case, the challenger select a random plain text instead of a 1-bit coin and generate the ciphertext by using this random message, and the adversary try to recover the entire plain text from the ciphertext. Okay. And in the case of indistinguishability, the advantage is compare the probability of the adversary output 1 in the case of the chosen coin is 0 or 1. This is the security of public key encryption with secure key leasing. We call key leasing attacks. Okay. We consider indistinguishability against key leasing attacks or one-wayness against key leasing attacks. This is the security notions for public key encryption with secure key leasing. Any questions so far? Okay, good. Before I explain how to achieve these cryptographic primitives, I explain the related notion called the single decryptor encryption, which is a stronger variant of secure key leasing. In this primitive, the company generates public encryption key, EK, and secret decryption key, DK, and generate, here, this is a bit annoying syntactic difference, but anyway, first generate classical public encryption key, EK, and classical secret decryption key, and then the company generate a quantum state version of this secret decryption key, and give this quantum decryption key to a user. And again, a sender generates a ciphertext of plaintext M1 by using, here is again, public key is EK. Encryption key EK by using public encryption. EK generate a ciphertext and send it to the user. Then the user can decrypt the ciphertext by using this secret decryption key. And that's it. There is no verification for the decryption key in single decryptor encryption. So the notable difference from secure key leasing is the security definition, which is called CPS-style anti-piracy security for single decryptor encryption, which is as follows. The challenger generates the public encryption key K and the secret quantum decryption key DK, and send these two keys to the adversary. And the adversary send the two challenge plain text and two quantum decryption circuit to the challenger. Okay? These are challenge plain text, and these two are kind of quantum decryption programs. And next, the challenger flip two coins, B1 and B2, and generate two ciphertexts by using these chosen coins and challenge plain text M0 and M1. One is encryption of MB1, and the other is encryption of MB2. And then send each ciphertext to each quantum decryption programs. And the point is that these two quantum programs cannot communicate each other. There is no communication between these two quantum programs. Then these quantum programs try to guess the chosen coin by the challenger. And if the probability these two guesses are correct is 1/2 plus negligible probability, then this is secure, anti-piracy secure. So why is the trivial security bound is 1/2 as follows? So because the adversary is given this quantum decryption key. So one of these two quantum programs can have this original decryption key as it is. So, okay, let's say this quantum program C0 has this original decryption key. Then this quantum program C0 trivially trivially can guess this correct coin B1 because this program has secret decryption key. However, if this adversary passes this decryption key to this program C0, then if it is unclonable, C1 has no idea about the other coin B2. So the trivial advantage of this adversary is 1/2. Okay? Yeah.
How do you ensure that these two programs do not communicate? There's something that
Yeah, these programs these two programs possibly entangled.
Yeah, so the question was how can we guarantee that these two programs do not communicate if they have some pre-entangled state, and for example they can use this entanglement to answer B1 prime and B2 prime?
Yeah, of course, these two programs are possibly entangled, but the point is that if these two programs can communicate each other, then that trivial attack strategy breaks this security, so there is no guarantee, right? Even if these programs are possibly entangled, when these two programs is given to this challenge ciphertext, they cannot communicate each other, then in that setting, if this advantage is 1/2 plus negligible, then we say that this is secure. Yeah, it's okay. Integrity is okay. But even in this setting, if the adversary cannot guess correctly these two bits, then we call it this secure. Yeah, of course it is possibly integrity. Yeah.
I think maybe this is related to what you were asking. Is there some sort of distance assumption that so like no signaling, for example?
Sorry, say it again?
No signaling assumption between the two parties? And then, so like even if they're entangled, if they're a certain distance away, then you assume that there's no communication?
No signaling means that they cannot communicate each other,
yes.
right? Yeah.
Yeah, so that's being assumed.
Yeah.
So like I think realistically, you assume that they're a certain distance away. I don't know if it's perfect, but it's like, yeah.
Thanks.
So maybe I can add to the answer. Entanglement alone is not enough to communicate because, well, you have to go a bit into the quantum mechanics, but if you measure one of the entangled particles, then the density matrix of the other particle doesn't change. And to, for example, perform quantum teleportation, which uses entanglement, you need to send a classical bit of information. And without sending that classical bit, entanglement doesn't allow you to communicate in any way.
Yes, of course, we cannot send classical bits via entanglement, but then we can increase this probability that we can guess B1 prime and B2 prime. And my question was whether we get the same negligible probability there. if the states were entangled.
Okay. Anyway, it's okay that these two programs are entangled. So it is allowed. Yeah. Okay. Question? Okay. So yeah, but yeah. Okay. Anyway, so this is a kind of unclonable secret decryption key. But we called it a single decryptor encryption. And basically, unclonability implies secure leasing. This is a very informal argument. We need to prove for each primitives, but in general, unclonability means secure leasing like this. So in this encryption case, if the adversary can break secure key leasing, then it means the adversary return a valid secret decryption key, which passes the verification algorithm. And at the same time, the adversary can correctly guess his chosen bit. Then these two objects, return decryption key and the adversary works as a good decryptors. Works as two good decryptors, so they can break the unclonability. Yeah.
So if I remember correctly, the single decryptor encryption doesn't provide a key verification algorithm. So what is the key verification here in this implication?
Oh, key verification. Okay. Okay. Actually, we need to look at the concrete construction. But for example, if we have the original secret classical decryption key, we can construct a projection to the original quantum decryption key. Then we can check whether returned decryption key is valid or not by using projection.
Okay, so you're saying there is a canonical way to build a key verification algorithm. Okay, thanks.
Yep. Thanks. Okay, so yeah, this is very informal argument, but in general, unclonability is stronger than secure leasing. So let's see the status of this field. There are many works on single decryptor encryption. So we can achieve this strong cryptographic primitive, like a public key single decryptor encryption by using sub-exponentially secure indistinguishability obfuscation, which is, of course, post-quantum secure. And there are many variants of this public key single decryptor encryption, like functional encryption, bounded collision-resistant variant, collision-resistant variant. But all these constructions need post-quantum indistinguishability obfuscation, because as Omri explained in this morning, which basically implies public key quantum money. So we need some strong tool to achieve single decryptor encryption. But however, if we consider some weaker variant of single decryptor encryption, like one-time secret key single decryptor encryption, then we don't need indistinguishability obfuscation. So, like if for single bit scheme case, we don't need any assumption. It is unconditional construction, Anand et al.'s work. And we can also achieve multi-bit scheme, one-time secret key single decryptor encryption for multi-bit plain text by using the LW assumption. One might think, maybe you think that if we can achieve single bit scheme, then immediately we obtain multi-bit scheme. But it is not the case in this setting, because neither the standard hybrid argument or hybrid encryption technique do not work in this setting, because the security definition is more complex than the standard setting. So we cannot apply the standard hybrid argument in this setting. Or in the single decryptor encryption case, we cannot use hybrid encryption technique because the decryption key is quantum safe. So it is not immediate to get multi-bit scheme from single bit scheme. Anyway, if we consider one-time secret key setting, we can achieve this primitive without using post-quantum indistinguishability obfuscation. So natural question is, okay, here, indistinguishability obfuscation is a very heavy tool, and we don't know concrete construction of post-quantum I/O based on well-founded assumption. There are many candidates, but the security is very heuristic. So the question is, because single decryptor encryption is very, very strong primitive. The question is, if we consider weaker variant, secure key releasing, then whether can we achieve public key encryption with secure key releasing from standard assumptions? That's the question. So far, so good? Okay. So now let's see how to achieve public key encryption with secure key releasing from standard assumption. This is the work based on Schwitter and other co-authors and myself. We can construct indistinguishability against the key releasing attack by using standard in the CPA secure public key encryption. And here's the roadmap. First, we obtain one-way carrier secure PKE from in the CPA secure PKE, and then lift one-wayness to indistinguishability. Now I explain the first part. This is a very simple idea to achieve a one-way carrier PKE from standard PKE. We use two keys of standard public key encryption. We generate two key pairs of public key encryption. And the quantum decryption key is superposition of these two decryption keys, okay? DK0 and DK1. Yeah, this is a superposition of these two keys. And the first register is just a distinguished bit. This is a DK0 and the DK1. And the encryption algorithm is as follows. We generate two ciphertexts of the same plaintext M by using these two encryption keys, EK0 and EK1. Very simple. And the decryption is applying the following unitary. This unitary look at these three registers. The first one is just a bit, which means we use EK0 or DK0 or DK1. No. Key for 0 or key for 1. Okay. And the secondary register is the decryption key. And the third register, we write these two given ciphertexts, CT0 and CT1. And we write the decryption result in the fourth register. So we run the decryption algorithm based on the first bit. We choose one of these two ciphertexts, CT0, CT1, based on this bit. We decrypt this ciphertext CTB by using the second register. And we measure the last register. Okay. If we can correctly decrypt these two ciphertexts, then we get the correct plaintext M by measuring the last register. So we can correctly decrypt this ciphertext by using these two ciphertexts and the secret superposition decryption key. Okay. How to verify this decryption key? We use projection. So secret decryption verification key consists of two decryption keys, DK0 and DK1. These are classical information. And from these classical decryption keys, we can construct this projection. By applying this projection to the returned quantum decryption key, we can check, this is a binary outcome measurement. And if projected onto this projection, then this is a valid decryption key. Yeah, by using this projection, we can verify returned decryption key is valid or not. So in this scheme, verification keys should be secret because it consists of 2 secret decryption keys. This is the simple idea to achieve a one-way carrier secure PKE with secure key leasing. Okay. Yes. Questions so far? Scheme is very simple, I believe. Okay. So the issue is this is secure or not. Okay. In the sense of one-way carrier security. In this simple construction, there is a trivial attack. Here is a trivial attack strategy. The adversary measures this superposition decryption key and can get either DK0 or DK1 with probability half. Okay. So then, the adversary, of course, can recover the entire plain text from one of 2 ciphertexts, CT0 or CT1. And this classical decryption key, it's not a superposition of 2 decryption keys, but we use projection that I explained in the previous slide. So this classical decryption key passes the verification with probability half. Yes. So this adversary can break the one-wayness with probability half. So if either of these decryption key, then the probability that the adversary can recover the plain text is probability is 1. So in total, this adversary wins the security game with probability half. Okay, so however, it turns out that this strategy is actually optimal. What the adversary can do is just measure this superposition decryption key and decrypt one of the ciphertexts. How to show? This is very non-trivial part. And we show this by using a new security notion, which is called consistent or inconsistent security. Okay. The scheme is very simple, but the analysis is non-trivial. What time? Okay. Questions so far? Okay. So again, this is a more fine-grained roadmap. We somehow achieve consistent or inconsistent security against key leasing attack, and we transform this COIC secure PKE into one query, one-way carrier secure PKE. One query means the adversary can send only once a verification query in the security game. And after that, we transform this one-way carrier secure 1 into int carrier secure 1. And then we can lift up this one query scheme to unbounded query scheme. From the next slide, I explain how to achieve one query, one-way security by using COIC security. Okay, I first explain what is consistent or inconsistent security. The challenger generates 2 key pairs of public key encryption. And the challenger sends 2 encryption keys, EK0 and EK1, and superposition of these 2 decryption keys. And the adversary can send verification query only once, and the challenger returns this given decryption key is valid or not. And then the adversary sends two challenge plain text to the challenger. Then the challenger flips two coins, A and B, and generates ciphertext CT0 by using encryption key EK0 and encrypt M1. So the adversary sends M0 and M1. And the first ciphertext is encryption of M1 under EK0. And the second ciphertext is ciphertext under EK1. And the plain text is M sub A XOR B. Okay? So if B equals 0, these ciphertexts are consistent because these two ciphertexts encryption of MA. Okay? However, if B is 1, then these ciphertexts are inconsistent because plain texts are different. M0 and M1. And the challenger sends these two ciphertexts to the adversary, and the adversary tries to guess the bit B, the coin B, not A, just guess B. And of course, the adversary can guess with probability half, but if this probability is half plus negligible, then we call it is COIC secure. Any question to this security notion? Okay. Okay. So let's see, before we see how to use this COI security to achieve one-way carrier security, let's see a simple fact. When we given this superposition decryption key and two ciphertext, which is ciphertext of M star under EK0 and M tilde under EK1, I mean these two ciphertexts are inconsistent, we cannot output DK0, M tilde, or DK1 and M star with non-negligible probability if PKE scheme is one-way secure. Why? Okay, let's see. So this means that if we measure this superposition decryption key, and for example, we get DK0, then we can recover M star trivially. However, we have no idea about the second ciphertext because we don't have decryption key DK1, so we cannot recover M tilde. And the other case is the same. So we can prove this simple fact by using pinching lemma, which was explained by Christian yesterday. Even if we measure this superposition decryption key in the computational basis before we give it to the adversary, this adversary has success probability at least epsilon over 2. So first we measure this superposition decryption key and give it to the adversary. This adversary still has success probability epsilon over 2, but by using the one-wayness of PKE, it is difficult for the adversary to recover the plain text which is not given to the adversary. I mean, by measuring this superposition decryption key. Okay. So yeah, this is a very simple fact by using pinching lemma. We want to use this fact to prove the security. How? Okay, this is a very, very high-level strategy to prove one-way carrier security. First, by using COI security, even if the adversary has access to the verification oracle, we can change the second ciphertext from encryption of M-star to encryption of M-tilde by using COI security. This is what is guaranteed by COIC security, right? And very intuitively speaking, if we measure valid return decryption key in the computational basis, we should obtain DK0 or DK1 with non-negligible probability. Okay. Of course, we need to prove this formally, but intuitively, if the decryption key passed the verification, it should be superposition of DK0 and DK1. And now we can prove one-way carrier security. So I slightly changed the winning condition of the adversary. So in the one-wayness, the adversary wins if recover the entire plain text. But even if we allow the adversary win if M prime is output plain text by the adversary, M star or M tilde. This slightly changed the one-wayness game, but this only increased the advantage of the adversary, so it's not a problem. Even if we allow this winning condition, we can bound the advantage of the adversary by using COIC security. Anyway, okay. So if one-way carrier security is broken, it means that the adversary output M star or M tilde. When this adversary is given CT0 and CT1, and if the adversary recover M star and M tilde, and we measure returned valid decryption key, we get DK0 or DK1 with non-negligible probability. Okay, this contradicts the fact. We cannot obtain, okay, let's see the fact again. We cannot obtain DK0 and M tilde or DK1 M star. So we can prove one-way carrier security by using COIC security and this simple fact. This is very informal argument, but this is a very high-level idea to prove one-way carrier security. Good? Okay. So, however, what we want to achieve is one-way carrier security, but this is just half one-way carrier security, which means that the adversary's advantage is half plus negligible. We can use parallel repetition to achieve negligible advantage. Just we use many key pairs to boost the security. Actually, so we divide the plain text M in lambda parts, and we prepare lambda pairs of lambda key pairs of public key encryption, and generate lambda superposition of decryption keys. And for each key, we encrypt MI, which is divided from the original plain text M. Yeah, we can use parallel repetition. However, the point is that we cannot boost the security from half one-way security to the negligible one-way security in a black box way. We cannot use like general theorem to boost the security. We need to look at this entire construction to analyze the security of full one-way carrier security. But this idea explained why our scheme is secure in the carrier setting. Okay. So good. We obtained one query, one-way carrier secure PKE from COIC secure PKE. The question is how to achieve COIC security. So before I explain how to achieve COIC security, I need to explain the important building block, one bounded ciphertext policy functional encryption. What is this? We have 4 algorithms. Setup algorithm generates the public key and master secret key. A key generation algorithm takes master secret key and some so-called attribute X and generate the secret decryption key for this attribute X. And the encryption algorithm takes public key and circuit C and generate ciphertext of this circuit C. And the decryption algorithm takes secret decryption key for attribute X and the ciphertext of the circuit C, then output some value Y. The correctness says that this decrypted value should be the output of circuit C that takes attribute X as input. Y is equal to C of X. And this is correctness. And here's one key security. This is a security game like this. The challenger pass the public key to the adversary, and the adversary query attribute X, and then the adversary given a secret decryption key for this attribute X. So the adversary can send only one query to the challenger, so we call the one key security. And the adversary send 2 challenge circuits, C0 and C1, and the challenger returns the ciphertext of C0 or C1 to the adversary under the condition that C0 of X is equal to C1 of X. Because otherwise, the adversary trivially distinguishes the ciphertext by decrypting by using given decryption key. And the adversary tries to guess the chosen bit. Okay, this is ciphertext policy functional encryption. And we construct standard public key encryption scheme by using this CPFE like this. We run functional encryption setup algorithm at the key generation phase. We generate the PK and MSK. And we also choose this random attribute X and generate a secret decryption key for this random attribute X. And the encryption key is this public key, and the secret decryption key is SKX. Very simple. And at the encryption algorithm, we consider circuit CM, which is M is hardwired in. And this circuit output M for any input X. Very stupid circuit, but it is okay. Because if we decrypt this ciphertext by using this secret decryption key, we get plaintext M. So this is standard public key encryption. Okay? No question? Okay, so we can achieve COIC security by using by this very simple scheme. Okay? And now again we look at the simple fact. Given 2 public key PK0 and PK1 and the superposition of 2 decryption keys SKX0 and X1. These X0 and X1 are random attribute. And we cannot output both X0 and X1 with non-negligible probability by using, again, pinching lemma. So if we measure this superposition decryption key in the computational basis before giving it to the adversary, we get SKX0, SKX1, and give it to the adversary. Then the adversary has no information about the other attribute, X0, X1. So the adversary cannot output both X0 and X1 by using the security of CPFE security. again, we use this simple fact to prove the security. And very important property of the public encryption scheme I explained is the tracing property. Is like this. So the adversary is given this public key for the encryption and the secret decryption key SKX. This is not a superposition version, that's just a simple classical version. And if the adversary, when the adversary is given encryption key K and decryption key DK, the adversary output 2 plain text and some possibly decryption program. Then the challenger check this decryption program by sending ciphertext by using challenge plaintext M0 or M1 and check this program's output. This program tries to guess the correct bit of the for the coin chosen to generate this ciphertext, and we check the success probability of this decryption program. Okay? So if the success probability of this decryption program is half plus 1 over poly, then we can show that we can extract X from this decryption program with probability 1 over poly. We can prove this property. I explain this why we can this from the next slide. But this is very important property to prove COIC security. Okay. So how to extract X from this decryption program? Okay, let's consider the following circuit C childer, where bit B, M0, M1, and index I are hardwired in. This circuit C childer takes X as input and output M sub B XOR XI. XI means the ith bit of attribute X. So I is hardwired in this circuit, so we can generate this output by using hardwired information and input. Okay? And we estimate the success probability of this decryption program by using ciphertext of C childer. Okay? So this is a ciphertext policy functional encryption. So we encrypt this circuit C childer by using the encryption algorithm. So we generate the ciphertext C childer and put this into this decryption program and check the output bit, bit prime, and we count the number of correct bit, bit prime, and we can estimate success probability of this decryption program approximately. Okay? Now, let's see the simple fact. This ciphertext of C childer is indistinguishable from the encryption of circuit C, where MBX or XI is hardwired. So let's recall the definition of C of M. Just output the hardwired plaintext. Okay? So here we hardwire MBX or XI. So this should output M sub BX or XI. Right? And this is exactly the same output of C childer for any input. Okay? So this satisfies the condition of security, one key security of CPFE. So these two ciphertexts should be indistinguishable from the adversary. Okay? So even if we give this ciphertext of C childer, the adversary cannot detect difference from the ciphertext of C where MBX or XI is hardwired. Then, how to extract information xi by using this property. If ith bit of x is equal to 0, then given this ciphertext is indistinguishable from encryption of MB, right? Because output is M sub B XOR XI. So if XI is equal to 0, then just this is MB. So if this decryption program correctly works, the estimated success probability should be greater than half, right? On the other hand, if ith bit of x is equal to 1, the ciphertext should be indistinguishable from plaintext M sub 1 XOR B, pretty version. Okay, now, then look at the success probability of this decryption program. Then this P shield should be less than half because it is flipped version of the plaintext. Okay? So, which means when we estimate success probability is this decryption program and look at this estimated success probability, if it is greater than half, xi should be 0. And if it is less than half, xi should be 1. And we can run this decryption program many times for all I. Then we can extract entire attribute x by using this decryption program. So if the adversary output the correct decryption program, then we can extract information x. Okay, this is based on the watermarking extraction technique against quantum adversaries of my work. And so actually this technique even worked against in the quantum setting, actually. Now we look at the classical case, but even if we consider the quantum setting here, quantum tracing property, we consider two keys, EK0 and EK1, and we send next we send a superposition decryption key to the adversary, and the adversary output to challenge plaintext, and now the adversary output the quantum decryption program because this adversary is quantum now. So even if in this setting, again we use but if we in this setting we use COIC security. So we need to, what we want to achieve is COIC security. So what adversaries do is correctly guess bit B in this COIC setting. And if the adversary generate this decryption program for COIC security, then we can extract x0 and x1 from this decryption program, quantum decryption program, with probability 1 over polynomial. We need some techniques in this quantum setting, but by using approximate project implementation technique by Chandry or Marriott-Waterhouse technique, and combine it with my watermarking extraction technique, we can do this. Yep. Good question. So, okay, so Hotek's question in the quantum setting, if we measure some output, that decryption state might collapse, right? But even so, that is a very good point. But I don't have much time to explain all the detail. But anyway, so even if we look at only the adversary success or not, we do not destroy too much that decryption program by using this quantum setting technique. Yeah.
CPABE, do you need quantum security?
CPABE, CPFE? Okay. Yeah, it is just post-quantum secure. Yeah.
You need quantum security.
Post-quantum security, just. Yep. Yep. Yeah, okay.
About the query, about the quantum query.
No, just the classical query, because the attribute is classical, and we don't need we don't need a quantum query by using our proof technique, actually. Yeah, great question. So it is a very big issue in the quantum setting. We might the quantum state might collapse if we measure the output of the degradation program, quantum degradation program, but we do not destroy too much. We can preserve the success probability by using those techniques. Yeah. Okay, so now let's look at how to achieve COIC security from this tracing property and the simple fact. So again, the simple fact is even if we give PK0, PK1 the superposition of these secret decryption key, we cannot extract X0 and X1, right? Now, let's consider COIC adversary. We gave 2 public keys and superposition decryption key to the adversary. The adversary send one query to the verification oracle. Now we just randomly guess this is correct or not. Then return this random bit to the adversary. And we correctly hit this valid or not with probability half. Okay. And the adversary send 2 plaintext, and the challenger, simulated the challenger generate 2 ciphertext, and the adversary guess the bit. Yeah. So if the adversary can correctly guess bit B by using this quantum decryption program, we can extract X0 and X1. If the adversary breaks the security, we see that we can extract X0 and X1. So this contradicts the fact. So we can get COIC security by using quantum tracing property and the simple fact. This is a very high-level idea. Okay, so finally, we can get one bounded CPFE, one key secure CPFE from standard in CPA secure PKE. So it is a well-known fact, so it's okay. How to bootstrap one-wayness to indistinguishability? We use Gold-Reich-Levin in the quantum setting. Yeah. It is well known that by using Gold-Reich-Levin's theorem, we can transform one-way secure PKE to indistinguishability secure PKE. In the quantum setting, we need to use quantum version of Gold-Reich-Levin, but it works. And I didn't explain the detail, but it is easy to bootstrap one query security to unbounded query security by using unreturnability. I didn't explain, but yeah, it is very easy to see, but so if you are interested in, please see the paper. I do not explain in this talk. And this one more unreturnability is preserved even in this quantum Gold-Reich-Levin transformation. So we can get unbounded query in the key area secure PKE from in the CP secure PKE. Okay? Okay, so that is a construction based on general in the CPA secure public key encryption. We can use any post-quantum secure PKE to achieve this in the key area secure PKE. There are, okay, so before move to other construction, we can extend this standard public key encryption to attribute-based encryption and functional encryption by using this PKE with secure key leasing. But yeah, I don't explain the details. But anyway, we can get FE version of secure key leasing. And there are other constructions of PKE with secure key leasing, which does not rely on the general public key encryption. They use LW assumption. Yeah? One work is announced et al. Use dual regF public key encryption to achieve this primitive. by using the LW assumption and unproved conjecture. And later, Anand et al. Improved this construction, improved the analysis. The construction is completely the same. The analysis is improved, and we can get this Dirac version from the LW assumption. The bonus of this construction is the certificate is classical. So we can delete superposition decryption key and generate a classical certificate to verify the certification is valid or not. And they also get other primitives other than PKE. They get FHE and PRF for, with secure key leasing, which is not achieved in the previous construction. We get FE, but do not FHE. And there is another construction based on VEGF PKE. Okay? They're slightly different variant, but yeah, they constructed PKE with secure key leasing by using RegF PKE. And the assumption is LWE. They use noisy trapdoor family in this construction. And the bonus of this construction is the communication is completely classical. We do not need to send quantum information to achieve this primitive. And they also achieve the FHE with secure key leasing by using the property of the LW assumption. Okay, so we have more time. So let's briefly see what the construction look like. Okay? So this is a dual RegF based version of the construction. It's basically the same as dual RegF encryption, but the decryption key is different. The public key is matrix A and vector Y. We look at many times in this school. And decryption key is now superposition of this short vector X. Right? First, we generate a superposition of short vector X, and then we apply the matrix A, and get A times X in the second register, and measure the second register. Then Y is fixed. Then this superposition state is a superposition of this short vector X, which satisfies this equation. This is used instead of a single vector X as a decryption key. And the intuition is like this. If the adversary returns a valid decryption key, then we can get, by measuring the decryption key, we get a valid preimage of Y. Okay? And if the adversary breaks the security, in the carrier security, then the adversary can distinguish ciphertext of the dual RegF ciphertext. Then we can extract preimage of Y by using substitute decision reduction. Actually, this is not easy part, very, very difficult and complex part. But intuition is like this. So if the adversary successfully distinguishes the ciphertext, then the adversary, we can extract preimage of Y by using this adversary. So we get two short vector of this preimage of Y. This contract is a cis, so it is secure. This is a very, very high-level intuition, and analysis is very complex. But yeah, anyway, we can achieve dual RegF version by using this strategy. Okay, let me conclude. So quantum states are unclonable in general. And we can achieve certified duration, secure key leasing, unclonable cryptography, many fantastic quantum cryptographic primitives by using quantum information theory. And the constructions are very, very simple on the surface. But the analysis is very complex. COIC security, I'm not sure whether COIC security is natural or not. But anyway, at least at this point, we need this security notion to achieve the end-carrier security from in the CPS secure public key encryption and the quantum extraction technique, which is used in the watermarking construction. Proving security is highly non-trivial. But I hope that we can simplify in the near future, which is a great open question. And we also have two approaches, general construction based on general in the CPS secure public key encryption, or we use the LW assumption. And in that case, we have several bonus achieving FHE or classical certificate, which was not achieved in the general construction. So there are pros and cons. Okay, that's it. Thanks.
Thank you. Do you have any questions to Rio? Hotek. Oh, Christian. Just wait.
Thanks for the nice talk. You mentioned that when you mentioned the other constructions, you mentioned that they also construct a PRF. So I was wondering whether that's difficult or whether you can just take a generic construction of PRF from PKE and
actually, I have no idea to achieve a PRF with secure key leasing by using general construction. Yeah, and so, but okay, so there is a construction of kind of unclonal version of PRF. I mean, yeah, PRF with unclonable evaluation key is achieved by using post-quantum IO. Which is, of course, secure key leasing version, could be a secure key leasing version. But yeah, so far I have no idea how to achieve PRF with secure key leasing from standard assumptions, which is a great open question, I think.